Good morning, all of you. We will start our session at 10:15 a.m. Good morning, all of you. Dr. Manish Gupta, sir, are you there? Dr. Manish Gupta, sir. Should we start the session?
Yes, hello. I think yeah, it was muted actually. Should we start? Hello, Dr. Mitlesh. Should I start?
Yes, yes, sir. Just a minute, sir.
Okay, sure.
Good morning, all of you. On the behalf of Information Technology Department of GCRC Engineering College, I welcome you all on the fourth day of the
Hello.
FDP on quantum computing.
Hello.
Dr. Manish Gupta, sir, is with us.
Good morning.
Let's start the session, and today's topic is quantum error correction. I
हाँ नहीं
request
एक्चुअली मैं भी अनम्यूट नहीं हो पा रहा था पता नहीं क्या हो गया था मैं इसे हाँ
I
हाँ
request you,
कर
sir,
दिया
to kindly start the
हो गया
session.
ठीक है थैंक यू Okay, so let me I think share my screen first.
Yes, sir.
So can you see my screen? I hope. Dr. Mitlesh, can you see my screen?
Yes, sir.
Okay, fine. Okay, so good morning, everyone. So let me start today a very exciting area of quantum computing known as quantum error correction. Quantum error correction is very fundamental thing. Without quantum error correction, as you know, it is not possible to make a quantum computer and doing anything. So not only quantum error correction is used for correcting errors or making a fault tolerant system, it has found also many interesting applications or connections with the different phenomena. For example, recently people have done work. For example, John Priscilla at Caltech, they have shown how this is connected to the black hole and maybe the Hawking radiation and so on. So really very interesting. So also from the point of view of understanding it and and from the application point as well, so let me start the talk. So what I'm going to do actually, I'm going to give you some brief idea about classical error correction because some people may not have an idea about error correction itself. What is this error correction business? And I'll show you that error correction is very
Sir, you are not audible.
yeah, actually somebody muted me actually.
Okay.
Now it's there. Yeah. Okay, so I think so now as you know, mm, that error correction is quite so. Whenever we are sending information from one place to other place, or whenever we are storing information from now to then, we require error correction. It's a very fundamental thing. Okay. Okay, so so let me talk about classical error correction first. Uh, so basically, I will talk about coding theory. So error control is everywhere in the engineering. So whenever we are doing anything, errors are bound to happen. So or similarly, whenever any information processing is going on, error correction is required. For example, I'm going to give you very simple examples. I'm speaking to you, and suppose you are not able to listen. So the first thing that you will say that please repeat, right? And so repetition is a crude form of error correction. It's a very basic form of error correction. So whenever I'm talking about something and you are not able to listen, so you say that please repeat. So repetition is a very crude form of error correction. We use it in everyday life. And so in the entire ICT domain, computer science and communication both, we so a lot of examples like phone, computers, internet, modems, mobile, GSM mobile phones. So no, we require error correction. So to process the data reliably, they use coding theory. Coding theory is a branch of mathematics with application in computer science and electrical engineering. Okay, and as I told you, redundancy is a very basic error correction scheme. So one can ask, how old is coding theory? I can take you 2000 years ago. Pingla. Pingla is a person, uh, uh, who has written, in this Chanda Shastra actually. He talks about, about computing the power of a number, x raised to power n. So you know that there is a very well-known algorithm that n can be written as a binary expansion, and then you do the calculations. So this representation of integers as a binary numbers is as old as 2000 years old, in India. Okay, so we can say that this is nothing but origin of binary codes. So essentially, binary codes are nothing but uh, just strings of 0 and 1. Okay, that's what we talk about. Now, this is a very famous picture, taken from the book Advancement of Learning by Francis Bacon in 1605. This is also known as common origin point for coding theory and cryptography. This is at the time of Shakespeare's. Well, people used to write secret letters. So they used to encode letters like A, B, C, D, E, F, G into these letters of A and B, symbols of A and B. So essentially, it's a binary encoding. And using this, you can actually write anything. But one important thing I would like you to notice here, that in this alphabet list, A is there, B is there, two letters are missing actually. So in English, J was not there and U was not there back in 1605. So this is an interesting fact I thought I should tell you. So you can see that, I is there, GHI, there is no J, then K, L, M, N, O, P, Q, R, S, T, U is not there, and V. Okay, so there were only 24 letters in English at the time of Shakespeare's. Okay, so it's an interesting thing. So for example, you can see that the spelling of county is COVNTY. Spelling of court is COVRT. There is no U. House is HOVSE. Okay, so this is the very interesting fact, Anyway, so this was further modified to what is known as 5-bit code by Bacon cipher, and you can see that I and J and U V are same. Basically, there is no separate mechanism to handle them. And this is a very famous picture. I think in the last session also I showed it to you. This is the first computer program written in the form of binary coded punch card. So here also binary codes are used actually for writing computer programs for operating these looms in 1805. Okay, another interesting development was done by George Boole by actually proposing algebra of propositional calculus. Okay, and also, so I would say that there was also some work on theory of electrical switches by Victor, and this I can say that, and Shannon's master thesis actually, so basically these three work, we can say that this was the starting of the foundations of digital age. So earliest digital electronic communication medium like printing, telegraph, and ticker tape, they used to communicate stock prices, and then in fact these two popular telegraph systems. The first telegraph printing text was David Hughes in 1856, and Thomas Alva Edison in 1869 used this golden stock ticker. The first stock ticker system using a telegraphic printer was given by Edward in 1863. So this in the 19th century, a lot of work has been done on this telegraph system, and that has resulted in this Morse code they used to do. So these are the some earlier version, American version, and international version. So this is a telegraph key they used in World War II. So some of you might have remember the Titanic movie, if you have seen there. So they have communicated using this telegraph key actually at that point of time. So this is the international Morse code which was developed. So you see this is D da da D D da D da D da D D D da D D da D, like this. You read this system, okay, and then this was further improved to what is known as teleprinters. Different models are available. Then Emil Bardut actually invented multiplex printing telegraph system, and the first electromagnetic telegraph was built by Carl Friedrich Gauss and Weber, and they used 5-unit code. So you see, by this time, you and I were there. J were there in the system actually. So now we have 26 alphabet by this time. So this was further, Bardut code was further modified to what is known as International Telegraph Alphabet number 1. And finally, this resulted into what is known as US ASCII code chart in 1968. And we are using these ASCII charts, now for encoding or communication with the computer. So all this is because of coding theory or, encoding. Now this there were major telegraph lines in 1891. These red lines you can see in the map, and actually, some of the people used to send data across these channels, and then they realized, they started asking questions: how much data can we send? What is the limit? And those questions resulted in uh, transmission rate. Actually, it was shown by Nyquist in 1924 that transmission rate is proportional to log of number of signal levels. And a lot of other work has been done in the area of telegraph, telephone, wireless telegraph, AM radios, television, teletype, spread spectrum. So major communication system before 1948, and around 1948, Shannon discovery happened. At Bell Labs, New Jersey. This is a Bell Lab, and at the same time, Richard W. Hamming, he used to work on a model 5 Bell Laboratories general purpose relay calculator. So he used to give calculations to this computer, the early days computer. And on Monday, when he comes back, and he used to see sometimes the machine stopped working because there is an error. And so he asked, when a machine can detect an error, why it cannot correct it? And that resulted in error correcting codes or error correction. It's a fundamental thing. Before that, people were not thinking in terms of error correction. So Richard W. Hamming is known as father of error correcting codes, and he has done a lot of work in this area. And one of his popular codes are known as Hamming codes, which he discovered, which was published later in 1949. So Claude Shannon in 1948 wrote a mathematical theory of communication paper. This was the birth of information theory. So information theory is a sister to coding theory. So information theory answers two fundamental questions, or I would say that it sets bounds on information storage, how much we can store and how much we can communicate. These are two fundamental questions that can be answered by information theory. So birth of data compression. So how much can you compress the digital information? The answer is information theory. Yes, so I think this was the birth of data compression. The birth of channel capacity. So people ask the question, what is the ultimate transmission rate of a digital communication? The answer is capacity C. And there is a fundamental result that given a noisy channel with channel capacity C and information transmitted at the rate R, then if rate is less than the channel capacity, there exists error correcting codes that allow the probability of error at the receiver to be made arbitrarily small. And this was the great discovery actually by Shannon, and that resulted in information error. Okay. So there are three kind of coding theory: source coding, where which talks about data compression; channel coding, we talks about error correction; and joint source and channel coding, sometime where we combine both of them. Some applications of coding theory. Now I will show you some brief applications, and that will, so that you have some interest. Deep space communications. You see that This is a picture of Mars spacecraft in Marine 4 spacecraft sent to Mars in 1965. And on the left hand side and right hand side, you see the picture, how hazy picture, because this picture was sent without any error correction. Okay, so now later on in 1969, I guess, and after that, they have sent several other spacecrafts, Mariner 6, 7, and 9. They sent improved pictures of Mars because of error correction. So now you see the clear picture. So they used error correcting codes here. So it's a nice example in deep space communications. Object tracking in physical internet is also possible by, like, all the barcodes that you see across your life in these days. It is because of error correction. This QR code that you see, or credit card, they use error detecting codes. All this storage, I have shown you this slide earlier. They use some form of error correction. Okay, so the question is how to construct codes. It's basically you use some combinatorial mathematics, algebra, algorithms, and then depending on the applications. So in most of them, we use redundancy in a very clever way. So now let me explain to you. So one part is done. Now I am going to explain to you about basics of classical error correction. So let me give you a very brief example how this technique works. Okay, so what I'm going to talk about is a repetition code. So basically, suppose I want to send the message yes or no. Yes means 1 or no means 0. Suppose I assign these symbols 1 and 0. And if I send was 1, what will happen? If the bit is flipped 1 to 0, I may not notice, and then the error may happen, right? So then I will receive incorrect result, which is no. So in that way, actually, if I only send 1 or 0, there is a problem. So people say that we should use redundancy. So we repeat it. So repetition code we use. So rather than sending 1, I will send 1, 1, 1. And rather than sending 0, I will send 0, 0, 0. 3 times repetition of the symbol. And now I send 1, 1, 1 across the channel. So what happens? Suppose we sent 1, 1, 1 across the channel. Errors will occur. And suppose the received vector is 1, 1, 0. Okay. So you can see that 1, 1, 0 is received. So last bit is flipped. So now what we know, the code that was sent was 0, 0, 0 and 1, 1, 1. Code is simply a subset of binary strings, so a set of binary strings. So now you see that 1, 1, 0 is received. I compare it with 0, 0, 0 and 1, 1, 1. So compare means I compute the distance between 1, 1, 0 and 0, 0, 0. Distance in terms of number of places they differ. So for example, distance between 0, 0, 0 and 1, 1, 0 is 2. They differ at 2 places, right? The first 2 places. And distance between 1, 1, 1 and 1, 1, 0 is 1. So they differ at 1 places. So that means distance of 1, 1, 0 with 0, 0, 0 is 2, and distance from 1, 1, 0 with 1, 1, 1 is 1. So that means I will conclude that 1, 1, 1 was sent because the distance is less. So using this distance idea, we can correct the errors. Similarly, if I send 0, 0, 0 and suppose 0, 0, 1 is received, I compute the error, I compute the distance from actual vectors which were sent, and then depending upon which one is closest, I decode the thing. Now here the distance turns out to be very important idea. For example, here the distance of the code is 3. So the distance of 0, 0, 0 and 1, 1, 1 is 3. So 3 is an important thing. Actually, if the distance of the code is d, we can detect d minus 1 errors and correct d minus 1 by 2 errors. This is an important theorem in coding theory. So now depending upon distance, we can correct how many errors. So for example, now in this, if 2 errors happen, suppose 1, 1, 1 is sent and we received 1, 0, 0, then we will not be able to correct. Okay, because we will have a wrong notion of thing. So that means we need to increase the distance. So if you need to increase the distance means we need to increase the redundancy. So rather than sending 0, 0, 0, I will send now 0, 0, 0, 0, 0, 5 times repetition and 5 times 1. So if 5 times 0 and 5 times 1 is there, so d is 5. If d is 5, so I know that 5 minus 1 by 2 is 2. So I can correct 2 errors. Okay. And so as you can see that the Hamming distance, we call it the distance or Hamming distance between these strings is number of places they differ. Okay. So this is the basic idea of repetitions. So if I want to correct single error, I repeat it 3 times. If I have to correct 2 errors, I repeat it 5 times. If I have to correct 3 errors, I will repeat 7 times, and so on. So people asked, is there any clever way? So this is a very crude form of error correction. We are just replicating the bits. Okay. So in mathematics, in coding theory, there are efficient way of doing these things. Essentially, our code is nothing but a vector space. I think Professor Jadip Mulekar has already given you an idea of vector space. So we know that, uh, over the binary field, we can think about the binary vector space, or over the finite field, we can think about a finite vector space. Okay. So those vector space are useful. So those vector space act as a error correcting code for us. So this is the one very basic idea about error correction scheme. So let me give you some a little bit more mathematical thing here. Any question, by the way, at this point in this error correction, please do ask me. Please do interrupt me and ask any question. Any question? Please, you can unmute yourself and then ask a question. Any question?
Hello.
Yes. Yes.
Good morning, sir.
Good morning.
Sir, you told that if we want to correct one error, then we use repetition 3 times.
Correct. Correct.
And when we want to correct 2 errors, then we repeat it like 5 times.
5 times. Yes.
So if we repeat it 5 times, then it may possible there are 5 errors.
Then I have to increase the length. I have to increase the distance. So if 5 errors will happen, so this code will not be able to correct. So this 5 repetition code can correct only 2 errors. If 2 bits are flipped anywhere, I will be able to correct. Okay. If more bits are flipped, so if 3 bits are flipped, I will not be able to correct. If 3 or 4, 5 will be flipped, we will not be able to correct. So we need to increase the length. Yes.
So at that time we also have to increase the length. So I want to know means किस level तक हमें length increase करते जाना है कि like
yeah, so
ये
तो अभी
bond.
Yes, so basically ये जिस तरह से हम कर रहे हैं, so as I told you right, अगर हमको distance d रखना है, यहाँ पे distance कितना है 5 है, distance अगर d है तो हम d minus 1/2 errors correct कर पाएंगे. Okay, so this is the relationship. तो यहाँ पे distance 3 था तो हम एक error correct कर पा रहे थे. 3 minus 1/2 is 1. Okay, distance 5 है तो 5 minus 1/2 I can correct 2 errors, right? 5 minus 1/2 is 2. Got it?
Okay.
So this is the relationship. Of course, there is a theorem. One can prove it. अभी यहाँ पे मैं proof नहीं करना चाहता हूँ, but at least I would like to tell you that this is the main result. अगर distance code का c है d है, तो we can correct d minus 1/2 errors. Okay, and of course this scheme is very elementary scheme. It's not very efficient scheme. There are efficient schemes available which will minimize, क्योंकि हम चाहते हैं कि लेंथ बहुत ज्यादा बढ़ाएंगे तो फिर हमारे लिए खराब होता जाएगा ना, जितना ज्यादा बढ़ाते जाएंगे खराब होता जाएगा. So we want to minimize, okay, we want to minimize the resources, right? So there are clever schemes available actually. So that is the whole branch of coding theory actually, error correcting codes. Okay.
Yeah, thank you.
Any more questions, or otherwise I can go further?
Yes, sir. I have a question. Like you said that as the error increases, so we have to increase the length to correct those errors.
Correct.
But in the beginning, like before, so do we have an information like if we pass this much length of code, so this much error will occur? Because if we pass a code of say length 5, so there could be 4 errors also. And
yeah, so then simply you cannot correct at that point. If there are more errors, of course the scheme will fail. I mean, the error correction. So that's why you see actually whenever we are using some applications, sometime because there is a limit how much we can correct. So so this is the limit for everything that is possible. So sometime so there is an error and then you don't have anything, you restart everything. So normally we ask for retransmission. That is another thing. So if we cannot do anything, we ask for the Yeah.
So with this method, there's no foolproof method. Like this is not a foolproof method.
No, it's a foolproof method up to certain limit, of course, but the engineering is all about that, so that we want to correct certain number of errors, so you have to use. So as an engineer, so people foresee, in the normal applications, then we design. So, okay, so we say that, okay, maybe, in so many cases, errors के chances को कैसे minimize कर सकते हैं, very minimal. So
Right.
we want to do that kind of thing, so that in most of the cases हम error correct कर पाएंगे. ठीक है ना?
Right.
That is the key thing.
Yeah. Okay.
Okay.
Thank you.
Okay. Okay. So now we go to the next step. This is the so I think finite field with q number of elements. So basically, what is field? Field, as there is a cricket field, football field where we play, right? Similarly, in mathematics, field means a set where we can play with numbers. We can play with numbers means we can play with addition, subtraction, multiplication, division. So that means we can do addition of two numbers, subtraction, multiplication, and division. All four are possible. Okay. So finite field means when the number of elements are finite in the set. Okay. So normally there are finite fields with q number of elements, and q is a prime power. So field is possible only if number of elements are some prime power. So for example, there is a field with two number of elements. There is a field with three number of elements. With four number of elements, there is no field. I mean, you cannot construct like this with Z3, but of course you can construct a field because 4 is 2 square. With 5 you can construct, 7 you can construct, 8 you can construct, 9 you can construct, 11 you can construct. So all the prime powers you can construct a field. So basically integer modulo n set will be a field. So now you see that in our previous example that we considered, C is equal to 0, 0, 0, 1, 1, 1, the field was Z2, which is 0 and 1. Okay. Only two elements, 0 and 1. Okay. So this is a finite field with two number of elements. So if we take field and take n copies of it, so cross product, we get a vector x1, x2, xn, where xi belongs to fq. So this is a nothing but n dimensional vector space, and our code is nothing but like this C that we took earlier is nothing but a k dimensional subspace of the whole space fqn. Fqn is a n dimensional vector space, and our error correcting code C is a k dimensional subspace of it. Okay. So this is a linear code. A non-linear code is there. So if you take two vectors in the code and you sum them, their sum may not be in the set. But whereas in the linear code, we have this condition that if you take two vectors, sum them, their sum will be in the set. For example, here in C is equal to 0, 0, 0, 1, 1, 1. If I add them, we get 1, 1, 1, which is in the set, right? This is a small example, but it is enough to explain to you that this is a linear code. Okay. So we can also talk about inner products. We can define inner product x dot y is x1 y1 plus x2 y2 plus dot 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 x and yn. This is standard way of inner product. Of course, everything is modulo n. Here everything is modulo some. In case of say binary, it will be modulo 2. And the Hermitian inner product is defined as summation I is equal to 1 to n xi yi raised to power l. So Hamming distance dh x comma y is number of places they differ, and d of c is known as minimum Hamming distance, which is minimum of pairwise distance among all. You compute the pairwise. So C is a code. C is a linear code. Suppose that means C is having bunch of binary vectors. So if it's a binary code, okay. So I just compute the pairwise distance and look at the minimum distance. So that is known as minimum Hamming distance. Okay, among all. So this distance is important for correcting errors. If this minimum distance is D, we can correct D minus 1 by 2 errors. Okay. So now let me give you some more idea. Dual code, so just like that, the vector space has a dual space because inner product we have defined. So we can talk about a dual space. A C perp is a dual of C. Is defined as all those vectors in the space such that inner product x comma y is equal to 0 for all x in C, and dimension of the C perp is n minus k if dimension of C is k. Okay, so this is n minus dimension of C. We say that C is self-orthogonal. A vector space is self-orthogonal if C is a subset of C perp. C is self-dual if C is equal to C perp. Okay, these are the important ideas in coding theory. Now, normally a linear code is defined by the parameters n, k, and d. So n is the length of the code. So length of the code means length of each code word, each vector that we did that is there in the set. K is the dimension, and d is the minimum Hamming distance. Okay. These are the parameters. As I told you, D determines how many errors we can correct. Now, any vector space has a basis. If you know linear algebra, so basis elements I can put in the form of a matrix. This gives you a k cross n matrix. Okay, and it can also be specified by a parity check matrix H, which is described by minus A transpose I in minus K, some standard matrix like this. Okay, so such that G is nothing but the linear combination. So basically, linear span of G is nothing but C, and C can also be described as null space of H. Okay, it is known as null space of H. So rank of H is n minus K. Okay, so this is the basic definitions about the. So any linear code can be described by two kind of matrices: generator matrix G and parity check matrix H. Okay, if the generator matrix I am using to describe the code, so the span of the G is nothing but C. If I am using parity check matrix to describe the code, then null space of H means Hx, all those vectors X such that Hx transpose equal to 0 is null space of H is nothing but C. So this is the relationship between G and H. And of course, if G is known, you can find H. If H is known, you can find G. There are ways you can do that. Another interesting concept is known as syndrome of a vector. If X is sent vector from C, remember we sent X equal to 1, 1, 1 and we received 1, 1, 0, right? So Y is 1, 1, 0, X is 1, 1, 1. Similarly, if X is sent, Y is received. Syndrome of Y is HY transpose. H is the parity check matrix, so syndrome can be computed as HY transpose, and this is really useful in correcting errors. So rather than this crude method of comparing each thing with each received vector with each vector, that is a really brute force. So basically, we actually do a much more systematic way of doing it. So let me explain. One such scheme is known as array decoding. Okay. So here, our generator matrix is 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1. There are two binary vectors. So two vectors are there. So their linear combinations will give you four vectors: 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, and the sum of them. So 1, 1, 1, 1. Here, remember, 1 plus 1 is 0. So 1 plus 1 is 0. Okay. So this is our code C. We have listed here. And the corresponding parity check matrix is this. I can compute. The code has parameters 4, 2, 2. Okay. So 4 is the length, 2 is the dimension, and minimum distance is 2. Okay. Now, once C is there, what I am going to do, I take one vector of a smallest weight, which is not in C, from the space. The space is Z2 raised to power 4. There are 16 vectors possible in Z2 raised to power 4. Z2 is binary field having 2 elements. So 2 raised to power 4 elements are possible, 16 elements are possible. I pick up one vector as 1, 0, 0 and add it to all of the vectors, all the codes in C. So I get 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, right? I take next vector as 0, 1, 0, 0, which is not in here, C and 1 plus C. So I add it here. I get another set of vectors. And finally, I add 0, 0, 1, 0. I get another set of vectors. So now you can see, interesting fact, all 16 vectors are here in the form of cosets. So these sets are known as cosets. A vector plus a code C is nothing but a coset. Okay. So this is the basically a coset. So now I think I should say that how do we arrive at C? C is nothing but 0, 0, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 0, which is a linear combination of the generator matrix vectors 1, 0, 1, 1 and 0, 1, 0, 1, where lambda i's are scalars in Z2. So I think I would like to first invite any question here before proceeding further. Please ask any question. Unmute yourself and ask. And I will show you how we can use it for correcting errors. But before telling that, is there any issue in forming this array? So we have formed this array by taking C. C is a linear code, and taking code, I have formed an array of the whole space. So whole space is decomposed into this array. And I'm going to now tell you how array can be used for decoding. Rather than individually received vector should be compared with every vector in C, we can do this array decoding. So we have partitioned the whole space into these vectors, and now we will use it to decode. Yes, any questions if you have, please ask. Otherwise, I will explain further. Any question? So if you have any question in the previous slide, I can go to the previous slide as well. If you have any question here, please ask, I can explain. Any question? So this is just some basic of coding theory, error correction techniques. Any question here?
So,
Yeah. No question? Okay. Okay, so let me come back to our explanation. So basically given a code C, which is here, which we formed using G1 and G2, two generator matrix elements. So what we can do now, actually I take this code and I form this array. Now let us see. Suppose 1011 is sent. Okay, 1011 is sent and we received y is equal to 1111. Okay, so some vector x is sent and we received vector is 1111. Then what we do? We take 1111 and look it into the array where it is. You can see that this green circle 1111 is here, right? So x is sent, y is received. You look it into the table. Where is y? I saw that y is here 1111. Now what I do? I look at this vector here which was initially added to form the array. I subtract that vector from here. So 1111 subtraction from 0100, and this subtraction is such that 1 plus 1 is 0. Remember, so 1 is same thing as minus 1. Is nothing but we adding this vector to this actually. If we add this vector to this again, we arrive at 1011 because this bit will second bit will flip because here it is 1. So 1 plus 1 will be 0. So we get 1011. So we decode this, that 1011 was sent. Okay. So if 1111 is received, 1111 is received, so I can decode it that 1011 is sent. So we corrected the error. Okay. Now I think I would like to ask you one more question, which is very interesting. But before that, okay. So now actually this array decoding, if you do it like this, again, you need to make this table, store the table and do the decoding. You write a program which will do this decoding and all. So there is another simple way. We call it as a syndrome calculation. So this is a syndrome column and syndrome of y is basically hy transpose. Okay. So syndrome of y is hy transpose. H is this matrix from 10101101 and y is, so if y is 1111, so y transpose is 1111. You multiply and you get this vector 0, 01 vector, right? So we can compute the syndrome. It turns out that syndrome of each vector here is 0, 0. Syndrome of each vector in this set is 1, 1. Syndrome of each vector here is 0, 1. And syndrome of each vector here is 1, 0. So this syndrome is enough. So x is sent, y is received. I compute the syndrome, see where the syndrome is. So that tells me, okay, it belongs to this. Okay. So I subtract 0, 1, 0, 0 from there. This is the error vector and we get the actual vector which was sent. Okay, this is how we do the decoding. Now, interesting thing to note that the distance is 2 here, right? So how many errors we will be able to correct if distance is 2? If distance is 2, I can correct 2 minus 1 by 2. That is 1 by 2. That means greater than 0, 1 by 2 is 0. So I will not be able to correct any error, right? Which is true. So actually I purposefully taken this example to show you that if the distance is 2, so in some cases we will be able to correct the errors. Just like this in this example, I have shown you if 1011 is sent and y is equal to 111 is received, we will be able to correct. But in some cases we will not be able to correct because distance is 2. Okay. So this is the key thing to remember. Okay, any question again at this point? Any question? Please unmute yourself and ask. I can repeat, anything you want.
So it means code of distance 2 are not useful.
Yeah, code of distance are not too useful. I mean, they can be useful only for detecting the errors. They can detect 2 minus 1. So code of distance 2 can detect 1 error, yes, but they cannot correct any error. So I mean, so what people use, why people use error detecting codes? Because in some situations, it is possible that, okay, if you know that error has happened, so you can ask to do the retransmission. So retransmission is done in most of those cases when error detecting codes are used in some applications. Okay. So if you really want to correct the errors as well, so you have to use the code with a distance at least 3, so that you can correct single error, or more than more than 3 will correct more errors, right? So that is a key idea here.
Okay.
Yeah. So this is a error correcting code. Any more questions about the error correcting codes? Now I'll go to little bit more. Okay, so now I think let me go one more. Now I'll show you how probabilistic decoding is done. So whatever we have done with respect to distance, it matches with the probabilistic decoding. So suppose we are having a binary symmetric channel. So means binary symmetric channel means 0 is sent and 1 is received with probability of error p. 1 is sent, 0 is received with probability of error p. 0 is sent, 0 is received with probability of error 1 minus p, because total probability sum is 1, right? Similarly, if 1 is sent, 1 is received with probability of error is 1 minus p. This is the symmetry channel, binary symmetric channel. There is symmetry in the probabilities. So now, if I use this repetition code 0, 0, 0, 1, 1, 1, so we know that the generator matrix is 1, 1, 1, and lambda times 1, 1, 1. If lambda is 0 or 1, we'll get these two vectors 0, 0, 0, 1, 1, 1. Okay, this is the generator matrix, and the parameters are length is 3. Each vector has length 3. Dimension is 1 because there is only one code in the generator matrix, one vector in the generator matrix, and distance is 3 because 1, 1, 1 and 0, 0, 0. The distance is 3 between them. Distance is 3. So this can correct single error, right? Now, suppose received vector is 1, 1, 0, and I have to check what was sent, whether 0, 0, 0 was sent or 1, 1, 1 was sent. Okay. So in general, we assume that the probability of error is between 0 and half. So here, say we can take probability to be p is equal to 0.05. Okay. So suppose received vector is 1, 1, 0. So what I do, I will calculate the probability that 1, 1, 0 is received and 0, 0 is sent. I will also compute the probability that 1, 1, 0 is received and 1, 1, 1 is sent. Okay. So here this probability is nothing but probability of 1 received 0 sent square times probability of 0 received 0 sent. Okay, because at one place it is 0, 0, otherwise it is different, right? So I can do this probability calculations. It turns out that the probability is 0.002375 if p is equal to 0.05. So probability that 110 is received and 000 is sent is this. Similarly, probability of 110 is received and 111 is sent is this 0.045125. Now this probability is more than this. That means 111 is more likely sent, and so this is how we decode. If 110 is received, I can say that 111 was sent by doing this probability decoding. This is known as probabilistic decoding. It is matching with our distance decoding thing. Both are same here. Any question at this point, because this is an important concept before we go to quantum error correction? Any question regarding this probabilistic decoding? Any question? So I'm just calculating the probability, what is sent, what is received, and then I decide whether 0, 0, 0 is sent, 1, 1, 1 is sent by depending on the probabilities calculations. Okay. Any question? Okay, so no question, then we can move further. Okay, so now we come back to our business of quantum computing. Okay, and so now I'll recall some of the things you already know about the qubits and so on. So you see, remember this slide I showed it last time, and I think Professor Jaydeep Murekar and Dr. Harish Rao might have already shown you various things. So this is the basis state. 1, 0 is a vector in C square. I call it cat 0. Similarly, cat 1 is 0, 1 in C square. These are the basis state. A qubit, single qubit is represented by cat q is equal to alpha times cat 0 plus beta times cat 1, where alpha and beta are complex numbers such that mod of alpha square plus mod of beta square is equal to 1. Right. So probability amplitudes are mod of alpha square and mod of beta square. Right. And normally a two-state system. So this rotating vector is our qubit. Ground state is cat 0 and excited state is, or another state is two-level system, another state is cat 1. So if you do the measurement of the qubit, we get 0 with probability mod of alpha scan, collapse state is cat 0, and we get 1 with probability mod of beta square with collapse state is cat 1. This is the basic idea about qubit and measurement. We can define similarly multiple qubits, 2 qubits. I am just recalling. It's basically, so qubit is a Hilbert space. So this is a 2 raised power 2 square 4-dimensional Hilbert space. In general, n qubit is a 2 raised power n-dimensional Hilbert space. Okay, Hilbert space is a vector space which is complete, right? And we can talk about inner product anyway. So now this is a general state is described as CB cat B. B is in 0 1. The CBs are complex number such that they satisfy this normalization condition. Okay, this you already know. So qubit evaluations, all operations of a quantum computer are linear. In order to preserve the normalization condition, the operations has to be unitary. So basic operations are single qubit and 2 qubit operations. So let me explain to you quantum gates. So this also you know already, but I'll just recall. Any unitary operator U from C square to C square is act as a as a single qubit gate. So there are specific cases like rotation. If R theta is this matrix and theta, R theta is a unitary matrix, theta is a number between 0 and 2 pi, it will switch the states like this. Theta equals 0 will give you I2 identity matrix. Okay, NOT gate is sigma x, or sigma x, or sometimes we also call it X gate. So this is 0 1 1 0 matrix. You can see that if you apply 0 1 1 0 matrix on 1 0, I will get 0 1. So it will switch the gate, So not applied on cat 0 will give you cat 1, and not applied, not a gate applied on cat 1 will give you cat 0. It's a bit flip. Okay, NOT gate. Then we have phase flip gate, also known as Z gate. So cat 0 will go to cat 0 and cat 1 will go to minus cat 1. Whenever there is cat 1, it goes to minus of it. And then there is a combination of bit and phase flip, which is sigma y is equal to I times sigma x sigma z. So sometimes we write capital X, capital Z, and capital Y, right? So this gate, if there is a cat 0, it will flip the gate and put it minus sign. Cat 1 will go to cat 0. Then we have a square root of NOT gate, which is 1 over 2, 1 plus I, 1 minus I, 1 minus I, 1 plus I. This is typical quantum NOT gate, such that square root of NOT into square root of NOT is a NOT gate. Hadamard gate is very, very important. H is 1 over square root of 2, 1, 1, 1 minus 1. It's a Hadamard matrix. It has the property that HS transpose is equal to Ni. So HS transpose is equal to 2I here. So now, if you apply cat 0 on H, you will get 1 over square root of 2, cat 0 plus cat 1. And if you apply on cat 1, you get 1 over square root of 2, cat 0 minus cat 1. Now, if I have to apply any of these single qubit operation on the jth qubit, that can be done as by writing the operator U as I2, 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 j minus 1 times U2 at the jth position, and I2, I2, I2 in the rest of the places, right? Where U2 is a 2 by 2 unitary matrix applied on the jth qubit. So this is how we can apply. If there are n qubits, I want to apply a single qubit gate on one particular jth qubit. So I can write it, I can apply it like this. Okay. So now this is a very popular gate known as control NOT gate. So you can see that this is a identity matrix here, and then we have a NOT gate here. So now how it works, if first bit, depending on the first bit, we decide what we should do with the second bit. If first bit is 0, don't do anything to second bit. If first bit is 0, don't do anything to the second bit. If first bit is 1, apply the NOT gate to the second bit. So 0 will become 1. If first bit is 1, apply the NOT gate to the second bit. So 1 will become 0. This is how control NOT gate works. A graphical notation is cat x1, control NOT gate, cat x1, and then x1 XOR x2. This is the matrix, and this is the diagram, the wiring diagram of the circuit for the 2 qubit gate. Now let me give you a very brief example of a circuit. Here is a simple quantum circuit. We have cat 0, cat 0, cat 0, 3 qubits. There is a Hadamard gate, there is a control NOT gate. So cat 0, 0, 0, applying Hadamard on first will give you cat 0, 0, 0 plus 1 over square root of 2 cat 1, 0, 0. You see that first bit is 0 and 1 combination, right? And rest of things are as it is. Okay. Then apply control not, control on the first and not on the second qubit. I can get 0. There will be no change in the first one because the first bit is 0. The second bit will change because the first bit is 1. So this will be 1, 1, 0 when applying control not. When we apply control with control on the second and not on the third, we get 1 over square root of 2 cat 0, 0, 0 plus 1 over square root of 2 cat 1, 1, 1. Any question? Any question with this quantum circuit? I hope by now you understand how to play with the quantum circuit. Yeah.
All clear, sir.
Okay, good. Fine. So now let us go to the quantum error correction. So now we are ready with the quantum error correction. So when actually Peter Shor started thinking in this direction, because when he gave the first algorithm in 1994 about the integer factorization algorithm, polynomial time algorithm, I think Dr. Harish Rao already talked to you about that RSA crypto system, right, and discrete log problem. So that you cannot solve with the classical computer. There are issues. I mean, it's very difficult. So when he gave the polynomial time algorithm, people started thinking, well, it is not possible to build the quantum error correction. So how will you do it actually? So then he came up with, so why people said that it is not possible. So let me explain to you that. So you saw that repetition code is 0 is 0, 0, 0, 1, 1, 1, 1 is 1, 1, 1. So is it possible to do the same for the quantum version? So quantum state is cat psi is equal to alpha times cat 0 plus beta times cat 1. Can I replicate this cat psi, cat psi, cat psi? So people said that this is not possible. The reason is no cloning theorem. You cannot do this in the in the quantum scenario. So that means we will not be able to. Why we cannot do this? Let me show you. Unknown quantum states cannot be cloned. This is a paper in Nature in 1992 by Wouters in Zurich. So the proof is very simple. So I'm giving you here. If cat psi is replicated cat psi, and cat phi is cat phi, then using linearity, cat psi plus phi should go to cat psi plus phi, cat psi plus phi. After opening this will be cat psi plus cat psi phi plus cat phi psi plus cat phi phi. Okay, so basically this is not equal to cat psi phi. So this is not equal to cat psi and plus cat phi phi. Okay, so this is because they are not equal, right? So that means because of linearity, unknown quantum states cannot be cloned. Okay. So the basic problem, 1 minute. Okay. Okay. So now actually there is a basic problem. Here is the storage transmission or stabilization of quantum states. Okay. And we want to transmit alpha times cat 0 plus beta times cat 1 to the quantum channels. Errors will happen, and so error states will come. Okay, so how to do this? Look at this. What are the basic errors? I2, of course, if there is no error, sigma x, not gate, bit is flipped, phase is flipped, or combination of bit and phase is flipped. So a general error operator E on one qubit is given by alpha time is a linear combination of all these matrices actually. And bit flip and phase flip errors are conjugate to each other by Hadamard transform. One can prove this. In fact, I'll show you in a much more detail about this relationship between bit flip and phase flip. Now, if you look at the array decoding, which I have shown to you for the classical error correction, right? That can be written like this. If C is a k-dimensional space of a FQN space, FQ is a finite field, the correctable error and the error syndromes are in one-to-one correspondence. I have shown you that errors and syndromes are in correspondence. And actually, set of all vectors of length n is partitioned into the cosets of the code as C union C plus E1 dot union C plus E Qn minus K minus 1, right? These are the error vectors. So error vectors we added onto the cosets. So if you remember, I'll just show you, Yes. You see, these are the error vectors we added to C. So get the whole partition. So I'm just writing everything in the form of notation mathematically. So this whole process of decomposing the whole space into these cosets is captured here actually. Okay, is captured here. So whole space is decomposed into these cosets. There is a disjoint union of these cosets, and there are total, how many cosets are there? There in the previous case there were four cosets that you can compute depending on the size of the whole space and size of the code actually, you know, the dimension of the code. So we can actually compute this. So this is really important. So remember, if X is sent, Y is received, we look at Y is in which coset. Depending on the coset, we apply the syndrome correction and do the decoding for us. Same idea we can carry for the quantum codes. So let me show you. I'll first give you the general idea, and then I will show you with examples how it can be done. So a quantum code is, we denote it by square brackets, you know, n comma k. It's a 2 raised power k dimensional subspace of 2 raised power n dimensional Hilbert space. And error acts by multiplication with a unitary matrix here. And the orthogonal decomposition of the whole space C to n is basically C direct sum U1 acting on C direct sum U2 acting on C direct sum U2 raised by n minus k minus 1C. So this is our decomposition. Just like in the classical case, we have the array decoding. Here in the quantum case also, we have a similar decomposition of the whole space. Okay. Syndrome measurements, we look at the EI and we apply the UI inverse to do the calculation, we get the C. So EI is equal to UI, C is a error space. Okay. UI times C is a error space, and when we apply UI inverse, we get the actual C. So this is how we do. Let me show you with a very brief example. If you look at the repetition code, so we know that cat0 cannot go to cat00, but actually we can say that alpha times cat0 plus beta times cat1 can be modeled to alpha times cat000 plus beta times cat111. So this is a kind of embedding of two-dimensional space into the particular two-dimensional subspace of the 8-dimensional space of the 3 qubits. So this is our, if you look at the left-hand side, we have C, and we have the decomposition of the, with respect to the repetition code. If 000111 is used, we get the repetition code like this, right? So if this as a basis we use here, the quantum version looks like this. Okay. So here actually you need C in the classical case. What happens if X is sent 111, suppose received vector is 101, you see 101 is where you subtract the error and you get the actual X which was sent, you know, which is 111, right? In the same way we can do for the quantum one also, you know, right? This code can correct one single bit flip. Okay. So if there is a single bit flip, you know, I can see which space it is, and I can actually go and apply the inverse of the error operator, and then I will get. So basically, so if error happens here in the 101, then I can apply sigma X on the second qubit to recover the actual which was sent actually, you know. So this code can correct any single bit flip, but it cannot correct phase flip. So there is an issue. But since phase flip and bit flip are dual with respect to Hadamard transformation, we can do the job of phase flip correction. So let me show you this example in a little bit more details in terms of circuits. So first I am going to build a 3-qubit repetition codes, okay, which can correct single bit flip. Okay, so 3-qubit flip code. So we have a quantum state alpha times cat0 plus beta times cat1. This is our qubit, and I want to encode it as alpha times cat0L plus beta times cat1L, which is a logical bit. So basically it is alpha times cat000 plus beta times cat111. So first thing I need to do when I want to do this, I need a circuit. I need a circuit which can take a single qubit like this and which produce these 3 qubits, you know. So what is that circuit? Circuit is very simple actually. Here is the encoding circuit for 3-qubit flip code. Here is our cat psi, which is alpha times cat0 plus beta times cat1, and then we prepare 2 n bits in the 0 state, and then apply control NOT gate. Control at first, not at the second gate, control at second, and not at the third gate. This I will show you will give us the output will be alpha times cat 0 0 plus beta times cat 1 1. Let us see how. So cat psi cat 0 0, we can expand it. It is alpha times cat 0 plus beta times cat 1, cat 0, right? So now if we take this second qubit inside, it is alpha times cat 0 0 plus beta times 1. So now when 1 is there, we are applying control at the first gate, not at the second. So because of this 1 here, the second 0 will become 1, right? Because not gate will be applied. So we'll have this alpha 0 0 plus beta 1 1. And then with cat 0 at the last. Then we apply control in the second and not at the third. So we apply again, we expand it. So first there will be no change, alpha times cat 0 0 plus beta times 1 1. So since second bit is 1, the last one 0 will become 1. So we get alpha times cat 0 0 plus beta times cat 1 1. So this is our logical bit that we got. So cat psi will be converted into alpha times cat 0 0 0 plus beta times cat 1 1 1. Okay, this is how we do the encoding. So this is the preparing of the logical bit, and the binary. This is again, it's like a binary. Yeah. So somebody has a question, please ask. Yes, unmute yourself and ask. Yes. Somebody has a question, please ask. Any question?
No, sir.
Okay, I think somebody raised a hand. That's why I was asking. Okay, fine. So basically, this is how we prepare the qubit. So now this we send this resultant 3 qubits on the encoded 3 qubits on the noisy channel, which flips the qubits. Remember, we are assuming that our channel right now is doing flipping the qubits. That's all. So now the flipping probability is p. So this it leaves bits unchanged with probability 1 minus p. Okay. So 0 bit cat 0 will become cat 1 or cat 1 will become cat 0 with probability p. And right, cat 0 will get cat 0 and cat 1 will get cat 1 with probability 1 minus p. Okay. So that is a noisy channel which flips the qubits. Now what to do? Now what will happen actually? When we do this, what are the possibilities? When we send alpha times cat 0 0 plus beta times cat 1 1 on this noisy channel, several possibilities are there. One possibility is there is no error. Another possibility is 1 bit flip happened. Another possibility is 2 bit flips are there. Another possibility is 3 bit flips are there. All the bits are flipped, So all these cases are written here. So first case is when there is no error. So we sent alpha times cat 0 0 plus beta times cat 1 1 and we received alpha times cat 0 0 plus beta times cat 1 1. Second case could be 1 bit is flipped. You see here the first bit is flipped, here the second bit is flipped, here the third bit is flipped. All these 3 cases are there where single bit is flipped. Then there could be 2 bits flipped, the first 2 qubit, the last 2 qubit, or first and the last 2 qubits are flipped. So we get 3 more cases. Finally, all 3 qubits are flipped. So alpha times cat 1 1 plus beta times cat 0 0 will receive, right? This was sent and this is received. So now I can calculate the probabilities. Getting everything correct is, if 0 is sent, 0 is received, the probability is 1 minus p. 1 is sent, 1 is received, probability is 1 minus p. So the probability will be 1 minus p whole cube to receive the first state, right? In each of these cases, the first 1 bit is corrupted. The probability is p times 1 minus p square in each case. So total probability is 3 times p times 1 minus p square. Similarly, to receiving 2 qubits in error, the probability is p square times 1 minus p. So total probability is 3 times p square 1 minus p. And similarly, all bits are corrupted. The probability is p cube. Okay. So these probability calculations are important, and I will show you how these are used again. Just like that, we have done the probabilistic decoding. I will show you how we can do the probabilistic decoding in the case of quantum error correction. Now, what we should do at the receiver end? So we sent Okay, we send this alpha times cat 0 0 plus beta times cat 1 1, and these are the possibilities with certain probabilities. Now the receiver will do what it will do. We add two more. So if you look at the classical thing, what we need to do in the array decoding, what we have done, we have calculated the syndrome. So can I do some syndrome calculation here? That's the question that we ask. Okay, and actually what we'll do, I will put two more Ankela bits here and as our syndrome calculation, and based on those syndrome calculation, we will do some corrections back to the 3 qubits which we received. So here is a complete circuit. So this was the encoder. Alpha times cat 0 plus beta times cat 1 was there, cat 0 cat 0. So encoder will give you alpha times cat 0 0 plus beta times cat 1 1, which is sent. And on the decoder is using these 4 control NOT gates, and these 2 Ankela qubits are prepared, and we are measuring the syndrome here. Measurement, this capital M is there, which will measure the syndrome. Now based on this what we receive here, we can receive 0 0, we can receive 0 1, we can receive 1 0, or we can receive 1 1. Depending on the syndrome calculation, we will go back and do some corrections back in these first 3 qubits to correct the errors. Okay, this is how the encoding and decoding is working. So let me show you what are the calculations of these. So 3 qubits and 2 qubits more, so total will be 5 qubits now. So our circuit was this. Cat psi L is producing this one, right? Then we have including 2 extra bits, Ankela bits, cat 0 cat 0. So our actual logical bit is alpha times cat 0 0 0 plus beta times cat 1 1 1, and then 2 qubits are there, cat 0 0 Ankela bits. So I can do the calculation here. I do the first control NOT and the first. Okay, so there will be no change here in the first one, but second one will change from 0 to 1 and 1 to 0. I think you do the similar calculation. So you will arrive at alpha times cat 0 0 plus beta times cat 1 1 and cat 0 0. So there is no bit flip. So you arrive at this case when there is no bit flip. Okay, this may be a possibility. Second possibility, so this was sent and this is received, there is no error. If one bit is flipped, so I flip the one bit and do the calculation, one bit is flipped, and we get alpha times cat 1 0 0 plus beta times 0 1 1, and the syndrome bits are 1 1. Here syndrome bits were 0 0 actually. So actually I can summarize all the calculations here. Okay, so received states with syndrome and probabilities. So this was sent. This was when there is no error, the syndrome calculation you can see is 0 0. Okay, and this is with 1 bit flip. All these 3 cases, syndrome calculation is here. 2 bit flips, next 3 cases, syndrome calculation is 0 1 1 0 1 1, and finally all 3 in error, syndrome calculations are here. So now I can calculate the probabilities also, and you can see that probability of the first state is 1 minus p cube, second is p times 1 minus p square, and so on. Last second, 5th, 6th, 7th cases are probability is p square times 1 minus p, and last case is p cube, because everything is in error, right? Now, if you look at the syndrome is 0 0 in 2 cases. One case when there is no error, and one case all bits are in error. So depending on the syndrome calculation, I took the syndrome, I saw it is 0 0. Then I look at the probabilities. Here the probability is 1 minus p whole cube, and here the probability is p cube. Now, as I assume that probabilities are less than half, I can see which probability is more, right? So actually, we will see that the first case is more likely to happen. So there is no error if the syndrome is 0 0 calculation, right? So this is the way we do the correction. If one bit is in error, actually I do, I look at again the syndrome correction. So you see, here are the details. So if the syndrome calculation is 0 0, no action, and the first case is 1 minus p whole cube, last case is p cube. If p is less than half, suppose probability is 1 by 4, I can compute the probability. So certainly first case is most likely to happen. So there is no error, right? If the syndrome calculation is 0 1, I can compute. There are 2 possibilities with the syndrome 0 1, and I look at again the probabilities, and then we do the calculation. Actually, we apply sigma x so after receiving this, choosing the state with the probability most likely to happen, and apply do the error correction by applying the sigma x on the third qubit. Okay, so third qubit is applied and the errors are corrected. So that is how you correct the error. Okay, if the syndrome is 1-0, you apply NOT gate on the second qubit. If syndrome is 1-1, you apply NOT gate on the first qubit. So all these calculations you can do and choose the states. So basically for each choice of syndrome calculation, there are two possibilities, and you choose the state depending on the probabilities. Okay, so something which is more likely to happen. Okay, and that is how, so I summarize it here. So the complete circuit for 3 qubit bit flip code is, this is the encoder. Single bit flip error is possible in the channel. So this encoder will give you alpha times ket 00 plus beta times ket 11, which is sent. And the last calculation of the syndrome calculation can be done with a single Toffoli gate. This is enough to do the calculations. Based on these 2 bits, it will decide when the NOT gate has to be applied. All those things can be summarized here. This is a simple circuit for correcting single bit flip in a single qubit. Okay, if our qubit is alpha times ket 00, if our qubit is alpha times ket 0 plus beta times ket 1, we encoded it in alpha times ket 00 plus beta times ket 11, and then this code can correct single bit flip like this, right? Now what happens if we do the phase flip correction? But before that, you can implement in the Qiskit. Actually, this diagram you can choose in the Qiskit, and actually here is a Qiskit implementation. So you can see that the headers are there as usual. I think Professor Jaideep Mulekar and Dr. Harish Rao might have given you enough exposure to Qiskit code. The first thing is here actually Q is equal to quantum register 3Q is actually preparing the quantum register, right? Basically. So initializes the 3 qubit register here, and then the second line here initializes the 1-bit classical register with this code, and the circuit is prepared by this step 2. Then control NOT gate is applied to Ankylia qubits. Then there is an error simulation is done by bit flip simulation is done by this circuit. Then we have simulating then applying again control NOT to Ankylia qubits, and then finally Toffoli gate is applied. CCX is a Toffoli gate, and then when we do the measurement actually, and based on this, so we can execute this. So basically, when we execute this whole Qiskit code, we arrive at this result. Output showing in the main qubit has been corrected to 0. Actually, this is how the output will be shown if you run successfully on the Qiskit. Okay, so now what about the phase flip?
Excuse me, sir.
Yes, please.
I have a question.
Yes.
Can you just show the circuit again in which we calculated the syndrome?
Yeah, this one.
No, like before that, like that was a simpler circuit.
Yeah.
This one. Okay.
Mm-hmm.
Yeah, I just wanted to see this.
Mm-hmm.
Okay, and my question is that in this case also, if we have a code with 3 qubits, so we'll be able to correct just one.
Yeah. So those distance things are there which we need to keep in practice. So actually, those kind of things are there because this will only be able to correct single qubit. So if you want to correct more, we need to increase the qubits. The same thing is there.
Right.
Okay.
So is this any better than the classical one? This implementation in quantum, is this any better than the classical?
How will you compare with the classical one? Because right now what we are saying that here also, rather than single qubit, we are using 3 qubits. And in the classical,
Right.
so basically it's the exact same analogy. The only thing is the architecture is different now. Okay.
Right.
In the previous case, it was simple architecture. Here, the architecture is different. So basically, the circuit is a little bit different as compared to the previous one.
Okay.
Right.
Okay, got it. Thank you.
And
Yes.
sir, I would like to know, this error correction, am I supposed to do after every operation or at the end of the operation? Let's say I'm using multiple gates in qubits. So this error correction, let's say for example, yesterday we were.
Yeah. Please ask. Yeah, please complete. Yeah.
Yeah, yesterday we were doing Shore's algorithm, let's say, for example. So I'm supposed to put this error correction before I do the measurement.
Yeah, so no, basically, yes. So if you are storing, see, the idea of error correction is very simple. If you are storing qubits on a quantum computer or you are transmitting, you have to do error correction. Okay. So this is a very basic thing. So basically, when we are building the circuit, we can also build the error correction circuit on the top of it, to do the error corrections. Otherwise, so in theory, everything is fine, but in practice, things will be different when errors will happen. Okay, so there is no way we can compute the errors, calculate the errors, unless we build the error correcting circuit in bit. So actual design will have the error correcting circuits as well if you are doing something. Okay, so whenever we are storing qubits, we need to do the error correction. Okay.
Yeah, so that error correction, like after every operation, we are supposed, let's say, for example, I have first qubit is there, I'm applying a Hadamard and then let a C naught. So some measurement probabilities I'll get. So after that, I'm supposed to put this error correction.
So that is, I think, that is a design issue depending on the engineer and how do you want to design your circuit actually, So basically, you can, I think, if you want to protect that bit, then yes, whatever qubit you have to protect, you have to have the error correction, right? So whatever qubit you want to protect. Okay.
Okay, sir.
Yeah.
I have one question.
Yeah.
If I'm implementing any circuit with the Qiskit on IBM experience, automatically IBM experience will add this on error correction.
Yeah, so error correction things are already there in the Qiskit, so you can play with it actually.
But if I'm doing it with QKit in my local, I should add in my circuit, right?
Yeah, so basically, see, if you want to understand the things, it is fine. I mean, without error correction also you can understand, just to understand how the basic circuits are done, say for Shore's algorithm or for any other algorithm, right? The understanding can be done. But in the real practice, things might be different actually, right? Yeah.
But just with 5 qubits, how can we implement the error correction? So we have to go for a
so we need to go for better version of. We have to go for better versions, of course. So there's a whole branch, I would say, of quantum error correction has been developed now. It's a very, very sophisticated area, and I will at the end I will show you how things are connected and what kind of things are done actually. In general, I will show you one result actually, which is used in general for quantum error correction. I'll show towards
yes, if you can show us one algorithm and then how it is merged or how these things are embedded, it will be great, sir.
Yeah. Okay.
Yeah. Thank you.
Hello.
Yes.
Sir. Oh, what is the n syllabit and why we use it? Means we use for decoding purpose.
Yeah, for the decoding purpose here. So for encoding, we use 2 n kilobits. So our actual qubit was single, right? Alpha times ket 0 plus beta times ket 1. We use 2 n kilobits for encoding and 2 for decoding. So these last two which we added is for syndrome measurement. Okay. Okay.
So n kilobit is always represented by this one, ket 0.
Yeah, so initially we prepare them on ket 0 and see what is the status, what happens after that, we do the calculations, then the circuit depends, right now here the circuit is control not, control not, control not, control. 4 control nots are used, right? From first to fourth and second to third, second to fourth and first to fifth and third to fifth, right? So this depends on the circuit, choice of circuit, what we are designing, what calculations we are doing actually. Okay. So now we go to, so now we go to phase flip. So as I told you, Hadamard gate converts phase flip and bit flip together, So basically, if there is a sigma x, you apply a Hadamard gate previous and after, you get sigma z. Similarly, if sigma z is there, gate, you apply a Hadamard previous and after, you get sigma x. So they are dual to each other. You can verify this with respect to by entering the corresponding matrix. So h is equal to 1 over the square root of 1, 1, 1 minus 1, and sigma z value you substitute, and you see how this will work. Okay. So this is a nice mathematical explanation to this, but this is the nutshell. Is a summary that Hadamard can be used to convert phase flip to bit flip and bit flip to phase flip. Now, how do we construct a code which can correct phase flip? Now, complete circuit for correcting single bit flip is this, which we have seen right now. Now, we can modify this circuit. You can see that the difference between this circuit and this circuit at the bottom is we have placed Hadamard gate before and after the phase flip error. So if there is a phase flip channel and a channel which has phase flip error, so this two Hadamard gate H here and H here, so there is a phase flip. So this converts phase flip to bit flip, and so we can use the bit flip circuit will correct the errors. Okay. Similarly, here H and H, here H and H. So detect phase flip, we add Hadamard at the end of the encoder and at the beginning of the decoder. This is a technique. This is used to correct the phase flip. So now you see this is a complete circuit for phase flip. So here is the implementation for the phase flip, and you can see that Qiskit code for that. You can simulate that, and the result will be shown to you. Now, actually, one important thing. So till now you have seen how to correct single bit flip or single phase flip, but how to get a combined code which can do any arbitrary single bit flip or phase flip. And that single bit flip or phase flip combination was done by Peter Shaw. He came up with an idea of 9 qubits. He said that to protect alpha times cat0 plus beta times cat1, you can spread them along 9 qubits, and the code is given here. This is the 9-1 code. So this is the basis state of the code. So alpha times cat0L plus beta times cat1L is the code which will protect any arbitrary single bit flip and phase flip errors. And actually later on people have optimized. They say that rather than 5, you can use 7 qubits are also enough, and somebody has shown 5 qubits are also enough. In fact, 5 is minimal. So if you want to protect single qubit, 5 qubits are required minimal to protect arbitrary bit flip and phase flip. By the way, I should mention that in the classical, you see that minimum 3 bits are required if you want to protect single bit flip. In the classical case, we were protecting only single bit flip. So minimum 3 bits are required to protect single bit flip by repeating 3 times. Here we have to use single qubit to be, if you want to protect single qubit, we have to spread it among minimum 5 qubits, and you have to give the code and circuits. So I'm not mentioning it here, but of course, in any quantum error correction chapter or something, and there are some review papers as well. If you want, I can share it with you also, where you can see how the circuits are built for 5 qubit codes or 7 qubit codes. For historical reason, because 9 is the first one which was done, so I have shown this code here, 9 qubit code. Okay. So now the question is, what will be the circuit for 9 qubit code? And here is the circuit: phase flip encoding, bit flip encoding, single qubit error, bit flip decoding and correction, phase flip decoding and correction. You can see the Hadamard gates are used and so on. Everything is a similar way we do. You see, bit flip, single bit protection, encoding and decoding, right? The whole thing can correct single bit flip and single phase flip. And I invite you to write as an exercise, you can write a program on Qiskit. It's a very good exercise, because now you understand for the individual cases, single bit flip and single phase flip. So now you can write a program by implementing this circuit in the Qiskit. It's a good exercise. So here is the implementation actually, and code I am not showing you. You can write the program on your own. Okay, so now connection to classical codes. I am going to tell you only one construction, as some people ask that in general, if you want to protect, how we do that. Of course, there are many schemes right now available, but I am just going to mention one of them, which is pretty good and very popular. This is known as CSS construction.
Sir, can you please show us a combination of a bit flip and phase flip?
Yeah.
Circuit?
Yes, this is the circuit.
So will it depend upon whose qubit I'm doing bit flip and whose qubit I'm doing phase flip?
No, so any bit can be corrupted, right?
Okay, whether it is bit or a phase, it can.
Yeah,
be
it doesn't matter. Yeah, that's a powerful code. Yeah.
Okay, and this is the optimized one.
Yeah, this is the 9 one. The optimized one is 5 qubit. You can use 5 qubit, so you can build a different circuit. So in fact, that's also, I think now it's a good exercise that can you build a circuit for a 5 qubit code? Of course, it is no given in the papers and literatures, but can you build a 5 qubit code? Now we know that it is possible, and 5 qubit is an optimal one. So if you want to protect 1 qubit, you will require minimum 5 qubit. Okay.
Okay. So is there any literature available wherein the circuit is given?
Yes. I can share one very nice review. It's about 80 or 90 pages, which talks about quantum error correction for beginners. Most of the circuits are given there, so you can actually look at it.
Okay, sir. Thank you so much. So blindly we can use that along with our own experiments.
Yeah, sure.
Okay, sir. Thank you.
So now the CSS construction is Calderbank, Shor, and Steen construction. That is a full form of 3 scientists. So what they have said, now actually the classical error correcting codes, as I have shown to you, that C is a k-dimensional vector space over some finite field. So if there are 2 codes, C1 and C2, binary linear codes with parameters, length is n, dimension is k1 and k2, and window distance is d1 and d2, such that so C1 and k1 d1 and n comma k2 d2, such that C2 perp dual space of C2 is subset of C1. Then if you look at the set omega j from 1 to 2 raised to power k1 minus n minus k2 is a set of coset representatives of the C1/C2 perp. Then these mutually orthogonal states psi j is equal to 1 over square root of mod of size of C2 perp summation C belongs to C2 perp ket C plus omega j. These states span a quantum error correcting code with parameters n, k1 minus n plus k2 of length n, dimension this, which can correct d1 minus 1 by 2 bit flips and d2 minus 1 by 2 phase flips. This is a nice construction. So given a classical code, I can construct a quantum codes, and I can use this code to correct arbitrary phase flip and bit flip in the channel. So of course, one has to build the circuits and so on, and a lot of things are there. So now people actually try to explore how we can construct the quantum code. So if you want to give you an example of a quantum code, we will give the basis of the space, right, or the circuit, whatever is good, right? And that's how we actually come up with the further relations. Now, actually, there are other connections, early connections by Calderbank, Eric Rains, Peter Shor, and Neil Sloan. They have written a paper with connection with orthogonal geometry in mathematics. This paper, Additive Codes over GF4, is a very famous paper by Calderbank, Rains, and Shor, which talks about a lot about error correcting codes using GF4. Stabilizer codes by Daniel Gottsman in 1997. He was a student of John Priskell at Caltech. He has written the first PhD thesis on quantum error correction. So you can look at his thesis available online right now. Daniel Gottsman is in Canada right now. And there is an abstract theory developed by Neil and Lefman in 1997, which talks about in general how we do the things. I have not gone into those details, but it will require a separate course on quantum error correction. There are so many things available right now, and some higher dimensional codes have been constructed, say from binary to query case. Some classes of quantum codes, and there are different kind of models have been introduced: symmetric model and asymmetric model. So Hamming code, hexa code, Reed-Muller code, Reed-Solomon code, convolution code, BCH code, LDPC codes. So in fact, most of the classical codes that you saw in classical error correction, there is a quantum analog now available, and people have studied them, encoding, decoding, and so on. So that's all, I think. Thanks. So if you have any further questions, I will be happy to answer.
Hello.
Yes.
Sir, a quantum code is nothing but that is a subspace of complex Hilbert space.
Correct.
If it is a NKD quantum code, then
so it's a 2 raised to k dimension subspace. Yes.
Yes. So I want to know that how code word of this code look like. Like in classical case, we take it there is subspace of that one.
Yeah. So the same thing, the basic example I have shown you here. This is a thing, alpha times cat 0L plus beta times cat 1L. This is a one code because the dimension is 1 here, right?
Yes.
So basically these are the basis basically, So k is 1 here. So 2 raised to power 1 means 2 basis states are there, right? One is cat 0L, another one is cat 1L.
Yes, yes.
So this is the basis. These are the bases. So actual code word is alpha times cat 0L plus beta times cat 1L. Here in this example.
Okay. So here we use like qubit. 1 qubit is a code word. 1 qubit is a code.
Yeah. So basically, it's a combination. So basically, what I'm saying that these are nothing but matrices. If you think, the cat 000,
Yes.
you can explain in terms of matrices, right? So you can do
Yes,
everything
yes.
in terms of Hilbert space, actually, precisely.
So like in classical case, like if we have a code like 313, so repetition code 313.
So the code is C is equal to 000111,
Yes.
right?
Yes.
So here, why I'm saying that the analog here is
Here is 913. This one is 913.
913. But
Yes.
this one and that one is little bit different because this is 2 raised to power 1 will be there here. You see,
Okay.
there K means actual dimension. Here the dimension is 2 raised to power. So 2 we don't write here, because it's clumsy. So we write only the value of K here. But this K and that K is different actually.
So here the elements of code word are elements of a complex Hilbert space.
Yeah. So here actually the basis state is this. So 0L and 1L will generate the code. So the code word is alpha times this plus beta times this.
Okay. Okay. Thank you.
So any more questions? I will be happy to answer.
Any more questions from participants? I think, sir, there are no more questions.
Okay. Thank you, Dr. Mithilesh.
Thank you so much, sir, for providing us information about quantum error corrections. Thank you, sir.
Thank you. So I'm stopping.
Sir, I have one question regarding.
Yeah.
So I have one question regarding quantum simulators.
Mhm.
Okay, and how error correction is done with the QSMs. So can you please shed some light on that?
No, so basically, depending on which simulator you are using, you have to write down the program for that. So basically, at a conceptual level, for quantum error correction if you want to implement anywhere, you need to have the circuits, right? So once you have the quantum circuit, and you know that most of the simulators work through these quantum circuits. So you have to write the code in the corresponding programming language. For example, in the Qiskit, you have to do the Python coding, right? I have shown you those codes. The similar way you can do and then do the simulation on that. Okay.
So as per say, if usually most of the simulators are 5 qubits or say 10 qubits.
Yeah. So right now, the companies are allowing only small ones. That is true. Yeah, and I think if I remember, probably Amazon is providing more, and maybe D-Wave is providing more. So I think I don't remember all of them, but I know, yeah, IBM is providing smaller ones. Yeah, so you have to try that one. Whatever.
Which simulator would you require for experimental implementation of different algorithms in our local systems?
No, so I think I would suggest. So if I look at, I have not tried all of them, frankly speaking, but I think IBM Qiskit is the good starting point. But I think Amazon bracket is also, I would say, is useful probably. So I think I have not seen that in details yet, but I think Amazon bracket, I whatever I heard about it, probably because it is giving more flexibility. So we may try that, or with the other ones, like Microsoft is also there, IBM. So all the big companies we can try, I think. So maybe I think I have to look at all of them and prepare which one is doing good. That I have somebody has to do the analysis for all of them. But
And sir, which one would be the open source one, which we can, edit after we like, as per our.
So I think see, these companies are allowing it for people to play, and I think the main purpose for them is it will be free as long as people are basically getting trained in the system, right? So once there are enough people who are trained in these areas, so then I think they may charge. I don't know, depending on, maybe for the initial things they are free for certain qubits, but if you want to go for higher qubits or something, or depending on the application, or maybe for the academic purpose it remain the free. We are not sure right now actually. Some of them they may start charging later on.
All right, sir. Thank
Sir,
you very much for the information.
Sir, how D-Wave systems are different from the Qiskit ones? What I understood from reading the material is they follow the annealing process, adiabatic
Yes,
annealing process.
adiabatic. Yes. Yeah. So actually,
So,
yeah, I think so. Basically, the hardware is different, obviously. So they are here they're using superconducting qubits. So I think I'm not expert in the hardware, but I think because D-Wave is, I know, is the first company which entered into the market actually. So when everybody, when even the IBM and other companies said that, well, it's probably is not possible. We should maybe should not do more. But I think D-Wave started because I think the main person who was the founder was basically from physics background, so they really spent a lot of time in building the hardware. So I hope they are doing in a more advanced. I think I heard that they are also going up to the 1,000 qubits pretty soon. So I think it's worth idea to look at the D-Wave systems, and see
yeah,
what they are
because
doing.
most of the optimization algorithms, they are doing it on D-Waves only. I don't see much of a work coming from Qiskit in terms of
Correct. Qiskit is basically, Qiskit is basically for starting learning, so you can play with the circuits and you understand things, and maybe then, I think we need to prepare. I mean, I need to prepare a lecture on, the comparison of all the platforms, which one is more suitable for what application. Maybe we need to do that actually as well, I think at some point of time.
Okay, maybe sir, instead of doing a comparison for everything, like it's again my idea. I'm not sure whatever I'm saying it is good or bad. Maybe two different things. One is Qiskit line of like what I believe Google and Qiskit, they all are gate based and everything, whereas D-Waves is completely different. So if you can let us know more about the adiabatic process and how they are doing, it will be really helpful.
Yeah, so I think that's one area in itself. I think for adiabatic error correction things,
Yeah, because I was wondering like how in adiabatic process the error correction and everything they must be implemented.
Yeah, so I think they look at some form of lattice and so on. It is quite involved. I think probably it requires a separate discussion actually. Yeah, but I think yeah. So especially for example, this topological quantum error correction has grown a lot. And so they use some sort of geometrical shape to do the calculations. So yeah, I think that requires a lot of I guess discussions and understanding.
Any more questions? Thank you, Manish sir, for a valuable talk. It is really helpful for the participants.
Thank you.
Thank you, sir.
Thank you. So I'm leaving now. Okay.
Okay, sir. Our next session will be start at 1 p.m. Our expert talk will be delivered by Dr. Harish Sahu. So join this group at 1 p.m. Thank you, everyone.